So generally, sometimes an integrand will have infinitely many singularities. This will happen if you've got 1 over a periodic function, and that periodic function can sometimes be 0. So we've seen, for example, that in the along the imaginary axis, things like the hyperbolic functions have zeros. Okay, so for example, cosh z has zeros at half integer, well, n plus I pi I, where n is an integer. So if we've got 1 over cosh, which, if you remember, is a reasonably behaved function, then that's going to have singularities, infinitely many singularities, located on the imaginary axis. So what happens if we want to integrate a function like that? The residue theorem strictly says that you have to have a finite number of singularities inside your contour. It's actually possible to get around that by taking a limit, but if we can avoid, in principle we could sum a finite number of singularities and then just take the limit, and that can work. But then if we take a limit, then we're taking a limit of an infinite sum. So ideally, we don't want to have an infinite number of singularities inside our contour. So, if the singularities are located on a line parallel to the imaginary axis, which could be the imaginary axis itself, it normally is, we use a rectangular contour of infinite length, like this one, where we take the limit as r goes to infinity. But importantly, it's got a finite height or finite width. So it only contains a finite number of singularities. So basically the idea is that this normally along here is the integral we want, I. Hopefully these bits here, as r goes to infinity, will tend to 0. That's really got to happen. And then the integral along here is a multiple of I. Now that multiple might not be a real number, that's not a problem, because then the final answer you get is, it looks like I might have missed out 2 pi I times the sum of the residues here. Okay, never mind. Okay, anyway, it's proportional to, it looks something like this, the sum of the residues divided by 1 minus lambda. So lambda might not be real, but that doesn't matter because 2 pi I times the sum of the residues will itself could be a complex number. May or may not be real, I should say. But so how do you, well, the key thing, the tricky thing in this type of integral is actually to choose w. So w is the height of this. And really what you do is experiment. You look at what you're integrating and you see what's the smallest w I can choose, so that this function here, when I integrate it, gives me the same integral as before, i.e. when w is 0, except it's multiplied by lambda, where lambda is not allowed to be 1. If it's 1, then basically this integral here is going to be minus this integral here, and they'll add up and cancel. Okay, so let's see how this all works with an example. So we want to find this integral here. Remember, sec x is 1 over cosh. So as I just said, cosh x has singularities at odd integer, half integer multiples of pi, I times I along the imaginary axis like this. So a reasonable choice, first guess, basically what you do is you look at the singularities first, and a reasonable, in a way you have to guess what w is and just try and see what different things give you. A reasonable first guess is to choose w equals pi in this case. It's reasonable because actually, well, remember sec x is 1 over cosh. Now, if you remember, cosh x plus I pi is simply minus cosh x. Okay, so cosh x plus I pi is simply minus cosh x. And when we substitute x equals, change x to x plus I pi in this thing, then we'll get something. So this is definitely going to be not equal to, lambda is definitely not going to be equal to 1. So that's good. So basically we're going to get something which looks like this, but then has an extra factor. And that's exactly what we want. Anyway, going into details. So this contour around here can be split into 4 integrals. Okay, so this basically, this first integral is the one we want. Then we've got this bit up here. Then we've got this bit coming back, which is very similar to this one, as we'll see. And then finally we have this one coming down, which is here. Okay. Okay. So I've said, okay, using cosh x plus iy equals this, you can simplify the third integral. Well, alternatively, you just remember that cosh x plus iy is equal to minus cosh x. What I've done here is I've got a minus sign. I'm using that to swap the limits r minus to minus r. Then I'm just writing this out in 2 bits like that. Okay. Now the second and fourth integrals tend to 0 as r goes to infinity. Since one of the exponentials is going to be always larger than, so importantly we've said that mod a is less than 1. So if we have a look at these integrals here, we've got e to the ar. The e to the a iy, because a is real, has modulus 1. Okay, a and y are real, so e to the a iy we don't have to worry about. We just have to worry about the e to the ar. Okay, so we've got an exponential e to the ar. Here we've got an exponential, basically cosh r means e to the r. So e to the r will always be e to the ar because a is less than 1. So as r goes to infinity, this will definitely, the integrand will go to 0, and the same with this. Okay, so we're safe. Both of these integrals will go to 0 as r goes to infinity. So we just end up with this integral plus this integral that we've rewritten. Then we know that this has to be 2 pi I times the residue of this, okay, which okay is easily calculated. Basically, it's p over q dashed. Q is cosh in this case, so q dashed is shine. So we just want e to the I a pi by 2 divided by shine of I pi by 2, which is the same as I sine pi by 2. So we just end up with e to the I a pi by 2 divided by I, and we want 2 pi I times that, and so that's where this thing comes from. And then where this thing on the bottom we're getting from, so 2 pi I cancels this I, the I and 2 pi I cancels this I. This thing on the bottom, this is basically coming from, we've got 1 times the integral we want plus e to the I a pi times the integral we want. which appears here. And if we simplify this, so remember how to simplify this. The easiest way is to multiply top and bottom by e to the minus ia pi by 2. Okay, so that then gives us the 2 here gives us 1 over cosh ia pi by 2. And we've just got pi left. Okay, so that's the answer. Okay, so you can now do question 22. Okay, in the next section, I'm just talking about using Mathematica to do integrals. Okay, it's just saying, okay, so the integral we've just done, you can do using this expression here. So this is good for checking your answers. When you come on to doing something like an integral like this, Mathematica can get into trouble because it doesn't know anything about these quantities m. I mean, in principle, m could be complex and so on. So you need to give it some information. So you can do that by saying, for example, well, the simplest way to say that m is real is actually just to add this line here, assumptions m is greater than 0 and a is greater than 0. Then Mathematica knows that both a and m are real. This is an integral we'll do a bit later. Just saying that sometimes Mathematica you have to experiment. I mean, this is saying that sometimes it's better to do the integral first and then simplify the result using assumptions afterwards. So yes, as I've mentioned here. So this is saying if you do these assumptions here, you get a complicated result. This might be with an old version of Mathematica. I'm not sure what it does now. But if you just do this and then simplify the result later and give all this information, which you can do with simplify, then you get the answer you want. So Mathematica is not amazingly smart. You have to help it along. Okay, so finish there.